the topic for today is going to be minimum degree of a Boolean. When I introduced this course, I told you that we are going to study functions like this, which are subsets of function like this, right? G is something where the range is real, F is something where the range is good. And one of the objectives is to see how this restriction helps us in figuring out the property. Today's lecture is going to tell you one such property. This property is going to be true for F, but not for G. What I'm trying to say is that this constraint that the function is Boolean is going to be important. Let me just start with some context so that we know what we are talking about. Obviously, all of you remember what the degree is. That is the highest or the biggest S for which Fourier coefficient is non-zero. The size of the biggest S for which Fourier coefficient is non-zero. That is defined as the degree, which is same as how you would define it in a real polynomial. This is the definition. Knowing this, can you tell me what is the degree of OR function or AND function? On, let's say, n variables. Sorry?
Degree n.
The degree is n. Why?
In the 0-1 representation, the degree was n for n.
Okay. Okay.
That's
Yeah.
only for-
Okay. If I don't allow you to use the 0-1 basis, then how can you show that or AND function has degree n? Or for that matter, majority, or for that matter, parity? How would you check whether the function has degree n or not?
We can write a Fourier expansion.
Okay, then yes. What does that mean then? That the degree is n or not? Forget about the degree of the function. Just ask it.
If every single if xi, if for all I xi can change the value of the function in some certain cases, then the degree should be n.
Are you saying that if the influence is non-zero, then the degree is n? If the influence is non-zero for all I?
Yeah, for all
That
I.
is definitely not correct. We will see that. What does it mean? I'm just worried about degree n. What does it mean that a function has degree n in terms of Fourier coefficients?
So there exists a Fourier coefficient f at s, which is not equal to 0, and then the coordinate of s is n.
How many s's are there?
Yeah, there is one.
Just
Yeah,
one.
yeah. Just
Just
one.
one, right?
Yeah.
Then I am asking whether this is 0 or not. Correct? Right? This is the entire subset. Is this notation confusing? This is 1, 2 up to n. And what is this Fourier coefficient? We know what Fourier coefficient. Yeah.
Inner product of f of x with the chi n.
Which is parity, right? Chi of n is the complete parity. So that means the simple question we are asking is, how much is the correlation between f and parity? On how many values f agrees with parity, and on how many values f does not agree. If there is a balance, if they are equal on same number of inputs as they are different on the number of inputs, then this value is going to be 0. Otherwise, In other words, you can easily find out for all these functions which you have studied, OR and majority parity, for all of them, degree of f is actually equal. When I should say the f is coming from these functions, OR and majority parity. For all of those, you will be able to see this. You can take it as a very, very simple exercise, but you see that it is easy to check, right? You basically just have to check whether parity and this function f, whether their values are agreeing or not. That's what you do. Make sense?
Yeah.
Right. Now, you might be thinking, as one of you already mentioned, that if this is non-zero for all I, implies degree of f is equal. Okay. To start with, forget about this. I will put this constraint very soon. Okay. Let me ask you, are there functions, are there Boolean functions whose degree is 0? Let me tell you that the question is actually very easy.
Constant Boolean functions.
Obviously, right? That is true, yeah. Degree 0, what are the examples? Two examples. Function f of x is equal to 1, no matter what x is. F of x is equal to minus 1, no matter whatever the value of x is. These two functions, exactly these two functions have degrees. What about degree 1?
Dictator functions.
Sorry,
Xi plus okay.
you have to make sure that the function is
I
Boolean.
mean, dictator functions are examples.
Yes, the only examples are dictator function or
Dictator function plus some constant.
no linear combination. These are the only functions, these are the only Boolean functions with degree 1. Sorry, someone was saying something, I stopped.
So can we prove that any linear combination of xi or minus xi would not be Boolean?
That is the question which I wanted to ask you. But now
Basically,
you have,
the value would go out of -1 and 1 range.
that is the intuition, but how will you prove it? Claim if f is a Boolean function and degree of f is equal to 1, then it is dictator or a negation. What are few of the results which we have seen for Boolean functions, but we have not seen? Great. So then we know, since f is a Boolean function, then summation f at s square is equal to. This is coming from Parseval. What can I say about this quantity? Come on, this is simple high school mathematics.
Are we using the AM RMS inequality?
Okay, so what do we know about this? This is greater than equal to 1. Can you prove this?
Yeah. So
Obviously,
Yes.
right? All of the f at s's are less than 1, right? Right. And if there are at least 2 terms, then f at s is strictly bigger than 1. Sounds good? The only ways summation cardinality of f at s could be equal to 1 is when there is a single Fourier coefficient whose value is 0. If there are two Fourier coefficients, then going from f at s square to f at s, I will increase the value, right? This is very, very simple statements about numbers, which people know in 8th class. So I'm not sure whether you didn't get it or it's too simple and that's why you're not saying it. Is this clear?
Yes.
Is there anyone for whom this is not clear? Okay, good. So now summation f at s is greater than 1. Now can you show that this function cannot be Boolean? There is a degree 1 function such that summation mod of f at s is greater than 1. The question is clear, right? We know summation f at s is greater than 1. We know it's a degree 1 function. We want to show that it is not Boolean. How will we do it?
So if f at s is positive, then the corresponding degree 1 variable will be 1. And if f at s is negative, then the variable will be -1. So
Very
one
good.
such, yeah.
You can just align value of xi's so that each term gives you the same sign. Everyone sees this? Right? Let's say whatever is the sign of the constant term, I will make sure that everything gets the sign of the constant. Then the value of the function is basically summation f at s, summation mod of f at s, which is not going to lie between minus. This is the contradiction, implying f can't be Boolean. Doubts about this? Are we okay?
So essentially, we are saying that if f is some alpha I times xi, summation of alpha I times xi, then each alpha I has to be either 1 or -1, right?
No. We are not saying. No. We are saying that we can choose xi so that alpha I xi has the same sign for all I. Your function is summation f at s chi sx. You know that this chi sx is just some variable xi or xj. Right? I will set xi such that, let's say f at s, if f at s is negative, then I will set xi to be -1. If f at s is positive, then I will set xi to be 1. That means this quantity will become summation f. This is what I'm saying.
Oh, okay, got it.
I'm not saying anything about f at s.
Yeah, got it.
Okay, you agree then? Then this claim is proved. Anyone who has a doubt about this claim? Okay, good. So now we know that the only functions which have degree 0 are constant functions. Only functions which are dictator, or only functions which have degree 1 are the dictator or negation. But this feels like cheating, right? Why does it feel like cheating? Anyone? Because really fx is equal to xi is just a function on one variable. It's not a function on n variables. You can add as many variables as you want in the definition of the function. It doesn't matter. But inherently this function is only a function on one variable. And that's why this is not a sound counter example of saying that every function has degree. Correct? Because it doesn't depend, the constant functions, the dictator functions, they do not depend on all n variables. You are adding extra variables without any reason. That way you can obviously make number of variables much more than the but that's a stupid trick. So the question which I should ask is, if my function depends on all n variables, does it imply that degree of f is? Make sense? This is a more obvious question to ask instead of the previous question we were asking, right? Questions? Okay. The question is clear, right? We have a Boolean function which depends on all n variables. Can it happen that the degree f is less than? Actually, first, is this Boolean really necessary? What if I remove Boolean?
If you remove Boolean, then the answer is obviously
False.
The answer is
That's the
obviously
sum
false.
of all
Yeah.
xi.
Yeah, you can just
Yes.
use any polynomial
Exactly. I
without
choose
using the top term.
very good. If I choose fx is equal to x1 plus x2 plus xn, it depends on all n variables, but definitely the degree is just right. So this Boolean is definitely required. Second question, what do we mean by it depends on all n variables?
Basically, influence of none of the variable is 0. Or I mean,
Very good. Very good. This is because if it depends on a variable, then its influence should be non-zero. Now
we
we have a,
equivalently say that the polynomial representation must have all the variables.
sure. Yes. Yes, that is equivalent. We now know that, right? Right. So now we have a perfect question to ask. We have seen that if f is a Boolean function and influence of every variable is non-zero for all I, does it imply that degree of f is? What do you think of this question?
I think it should not be true because I mean, in terms of if it has squares, the summation how influence of if comes, we can say that we can I mean take like we can choose some, let's say some k elements 1 to k, so and choose k sets we can choose so that they have all of their different distinct k possible sets, and so and then we can make all of them non-zero, and then the influence would be non-zero for all, but the degree would be less than equal to k. So
Will that be a Boolean function?
we can choose our FATS like that. So
You haven't shown me such FATS.
okay.
Just conjecture. My claim is that no, you can't choose FATS. But you are going in the right direction. See, actually, degree f equal to n is a very, very simple question. Right? Degree f equal to n is basically asking the question whether this is sorry, 0 or not, right? This is something which we have already seen. We are asking what is the inner product of f with f. Right? This equivalence is clear. There is no doubt about it. That's the definition. I should say not equal. Right? That is equal. If the inner product is not equal to 0, then degree f is equal to n. If the inner product is 0, then the degree f is less. I will leave it to you to show that there exists f. There exist many f's actually, such that f, this inner product, is not. Okay. When you have put this question in the standard basis, this will become very, very easy. This is only asking whether at how many places f agrees with that. And that you can make it agree with any number. Your entire space is the entire Boolean functions, right? So you can let your function agree with parity how much ever you need, in some sense. And that's why this quantity could be almost any real number with some granularity, like any rational number with the denominator being to the power n, something like that. So this is not a very difficult question. What we got the answer as yes, there exists f such that degree of f is less. Does this sound believable? Anything which is not clear? This exercise you can do it later, but assuming that exercise, then you are sure, right? Whatever we are doing is correct. Any questions about that?
I think in the exercise you should write equal to 0.
Oh, sorry. Yeah. Thank you. Yes. You guys are smart enough for these kind of typos, right? Yes or no? That's a tricky question, right? So yeah, these typos you can fix. That's what I assume. Okay, good. What do we know about Boolean functions? Again, there are Boolean functions whose degree is 0 or 1, but they are these trivial functions which do not depend on all n. The question to ask is, if f is a Boolean function and influence I of f is not equal to 0 for all I, then what is the question I'm going to ask? What do you think?
Where is the degree n?
What is the minimum possible degree, right? We know that for some functions it could be n, for some functions it could be n minus 1. But how low can it get? This is the question. Is the question clear?
Yes.
Minimum possible. What is your guess? Okay, let's play this fun game. Everyone will give a guess. Anu, if you know the answer, then just say, I know the answer. You don't have to say it. But otherwise, you have to take a guess. Anu, what do you think? What could be the minimum possibility? You have to unmute yourself, Banu.
1.
Okay, 1. Incorrect. Aditya,
n/2?
incorrect. Anindya,
n/2.
I already told it is incorrect. You had a chance to be. Now you can't take another chance. You had a chance. Ashish. Ashish, you are muted. Debarsho.
So some kind of small o of n.
Yeah, you have been very safe. That's a no. You have been more precise than that.
Yeah, log n or root n, something like that.
Okay, okay. Dhanvit, Dhanit, sorry, I'm sorry, Dhanit.
I think it should be n.
N, okay. Udit,
n/3.
okay. Vatsal,
n/4.
okay. Yatin,
I think it's n.
okay. Is there anyone else who is left? Everyone answered, right? Okay. So only one person answered, but he answered because he was very, very
Sorry,
safe.
my answer was not heard. I said root n. My was off.
Okay. So Ashish's answer is also incorrect. What we are going to show is that for every such f, degree of f is going to be more than. Also, there exists a function f such that degree of f is odd. So Devarsho had taken a correct guess, but I think it was cheating in some sense, right? He was saying small o of n, then saying trying all many functions. But anyway, can you, okay, now once you know order of log n, can you think of a function for which degree of f is order of log n? I haven't introduced that many Boolean functions, right?
Address.
Yes. Again, this is a small exercise. You will show that for addressing function, degree is actually log n plus. Just remember how we created the function using truth table. Just do that. You will see that the degree of the addressing function is log n plus. We are going to show that you cannot get a better degree. You cannot have a smaller degree than the addressing. By the way, most of you were guessing order of n by 2, n by 3, n by 4. This is something which we will not do in this course. Probably one of you will take it as a project, but for a symmetric Boolean f, if we also say that function is symmetric, not just that its influence is non-zero everywhere, we say it is symmetric, then degree of f is very, very close to n. You know how close to n? N minus n to the 5. But that requires an additional constraint that the function is symmetric. So it is more than n by 2, it is more than 9n by 10, it is more than 999n by 1000. It is very, very, very close to, but this is for symmetric. This paper, this is paper by Gathan and Roche. And this is given as an extra. This is given as a project. If one of you is interested, you can feel free to take this. Okay, now our task is clear. We want the proof of theorem. If the function is Boolean, not necessarily symmetric, just Boolean, then its degree has to be more than 1. Everyone happy with what we have discussed till now? Any questions? Are you ready for this? Ready for the proof? What happened? Everyone sleeping?
Ready.
No, sir.
Ready? Not ready? Why?
Not sleeping.
Okay, not sleep. Okay, okay, that is good to know. Okay, yes, we want to do the proof of theorem, and the condition is clear. There is a function which depends on every variable. If its influence is non-zero, then the degree is order of n. The proof requires two important facts. First is that the total influence of a function is less than or equal to its degree. Second thing is that if degree of f is small, or I should say, if degree of any function g is small, then either g is equal to 0 or probability that g is equal to 0 is small. Okay. Let's just go over these two ideas. First is a very, very mathematical Fourier expression thing. Influence of f is less than equal to degree of f. How many people already see the proof of this? How many people see the proof now?
Yeah, I can see that.
Right? So can you tell me why?
So influence of f is all such s is the summation over all s of cardinality of s times f at s square. So we can write this is less than equal to maximum of cardinality of s times the summation of f at s square, which is maximum cardinality of s.
Right?
Yeah.
This is Parseval. This is one.
So
Right? We always remember, yeah, last time it was pointed to us that f at s square is a probability distribution over the sets. That means summation f at square is equal to 1. Now, if the maximum value you are allowed to put on f at s square is degree of f, then the summation cannot be more than degree. Right? That means this is an easy thing to do. Any questions about this part? Influence of f less than equal to degree. Everyone is fine? Okay. Since everyone is fine, let's move on to the other idea, which I will write as a claim now. What am I saying? That if there is a small degree function, either it is going to be 0 everywhere. Otherwise, there are few places where it is 0, or there are a lot of places where it is 0. If degree of f is equal to d, again, it is Boolean. Actually, you don't need the Boolean criteria now. If degree of f is equal to d, then and f is not identically equal to, that means it's not a 0 function. It doesn't take 0 value every. Then probability over x, f of x not equal to 0 is bigger than 2 to the power. Are we fine with the claim of the claim? Do we understand the claim? Remember, this probability increases as d decreases. If you know that the function has only degree 1 and is not identically 0, then it has to be non-zero at least at half of the x. Okay. If it is 2, if the degree is 2, then it has to be non-zero at least at 1/4 of the x. If the degree is d, then it has to be non-zero at least at 1/2 to the power d fraction of the x. Again, remember here, f is not a Boolean function. Okay, f is any general function. I mean, from -1, 1 to the power n. That is why I'm talking about being not equal to 0. Otherwise, if it was a Boolean function, it could never be equal to 0. the meaning of the claim is clear. Can we go to the proof? No one says yes or no. See, I can't see your
Yes.
faces. So please, someone take the initiative and say yes or no, so that I know I can follow. Right? In the regular class, I can see your faces and I know that whether you did not understand it or whether you got it. So in this online model, you have to help me. Right? Good. We can go ahead, right? I want to prove this statement that if the degree is small, then there are many places where the function is not. How am I going to prove it? I'm going to prove using induction. And if you were not, if you were attentive in last yesterday's class, I told you how to apply induction on functions. Remember? What was the idea there?
Set one input as, I mean, fix it. I mean, remove one of the variables
And then what is left?
an n minus one variable function.
You were there in yesterday's class. You can be more specific about what function will remain.
I mean, f of x1, x2. I mean, at xn you put one.
No. You remember the derivative and the expected value function? We talked about this, that I can write my function as xn times derivative of f at nth variable plus en of. This was nth variable set to 1 plus nth variable set to -1 divided. Right? Now, when I remind you, now it is clear. Actually, the definition of DNF and ENF is not that important here. What I'm doing is I'm looking at the expansion of f, just collecting the terms which have xn. Take out xn. What I will be left with is DNF. And then there are terms where xn was never involved. That is called en. Okay. To remember DNF and ENF, in spite of their names, do not depend on
xn.
xn. Now, there are two cases. Let me just, okay, I will go to the case analysis later, but xn has two settings, plus minus 1. Depending on that, f will become DNF plus minus, I should say, okay, plus EF, right? That depends on x. Now, case 1, none of is identically zero. It's not, they are not zero function. Okay. If this is the case, then my claim is things are simple. Can you guess why? Now, suppose I give you this extra condition that ENF plus minus DNF is not, is not identically zero. Then can you apply induction?
For half the inputs, I mean, we can
Good.
say
For half the inputs, my function will become ENF plus DNF. By induction, sorry,
nothing.
what is the induction on, by the way?
On the degree,
No, it is
Number of
on the
inputs.
number of variables. Very good. It is on the number of variables. If I look at on the degree, I will get stuck. It is on the number of variables. Now, what is the probability for ENF and DNF to be 0? By induction, what is the probability? What do I know about ENF and DNF? Its degree can be at most
n minus 1.
2
So
to the
now
power
No, its
D
degree
d
can be
minus
at most
1.
d.
Yeah.
No, it can be df also, right? ENF can have degree d also, right? So ENF plus minus DNF, it might happen that its degree is d minus 1, but it can at most be d. That you are sure of, right?
So by
What
the
is D? What is the degree of F? The degree of F is D, right?
Yeah, degree of f is d,
Okay.
right?
So how
So,
can degree of ENF be D? I mean,
oh,
that degree.
take
Oh,
x,
okay, it is
xn plus x, x2, x3.
possible.
Okay, right? The degree of f is 2. The degree of ENF is also 2. The degree of DNF is 1. Sounds good?
So
Yeah.
what do you mean by none of ENF plus minus DNF? So there are two possibilities, plus DNF and minus. Out of these two, none of these two is identically zero.
Yes, that is
Okay.
what I'm saying. So there are two functions, called them g and h. G is also not identically 0. H is also not identical. Okay. Now, since ENF plus minus DNF, so half, right. So then the probability that ENF plus DNF is 0 is to the power minus, right? Because the degree cannot be more than d for sure. That you can be sure. This half corresponds to the case when I take xn to be 1. And then this corresponds to the case when I take xn to be minus. Again, in this case, since the function is not identically 0 and the function's degree is d, it will be non-zero at least with probability to the power. This tells me to the power. This case is done. Questions about this case? I have talked of this in terms of probability. If fractions help you out, then there are half inputs for which xn is equal to 1. For all of those fraction of inputs, at least to the power minus d, for at least to the power minus d, the function will be non-zero. Similarly, for xn equal to minus. That's why this is the total fraction of numbers for which f is non-zero. This proves case 1. This is the easy case. That's okay. If there is any doubt, tell me which statement is not clear. I can go over it again. Should I move forward?
Yes.
Okay. Anyone? Last thing was not clear to them. Is there anyone? Okay. Let's take case 2. Suppose DNF minus ENF is equal. Or if you want, I can put it this way. When I set xn is equal to minus 1, the function tends to 0. Obviously, both cannot be identically 0, right? Both identically 0 means DNF is also 0, ENF is also 0. That means f is equal to 0. That cannot happen, right? Only one of them can be equal to 0. This is also quite clear, right? What I'm saying is, can this happen? Why can't this happen? Both of these simultaneously. Why can't this happen?
Because that would imply
would
F
make
is identically
F is
0.
0. Yes.
Right. You add them, you will get ENF is equal to 0. You subtract them, you will get DNF is equal. That means F is identical. This case is out. We are only left with this minus DNF plus ENF equal to 0. The other case is similar. I will not go into. When DNF plus ENF was equal to 0, That is other case, but it is very similar to case 2. We won't go into that. Now, for half the inputs, already the function is 0. When I set xn equal to -1, the function has gone to 0. But now what happens for xn equal to 1? Now, minus dnf plus enf equal to 0, this implies enf is equal to df. This implies f is xn Sounds good?
Yes.
Yes.
Right? This is simple because ENF is equal to DNF. Other way to say it is when I put xn is equal to -1, the function becomes identically 0. And we know what it means in the real variables, right? It means that 1 plus xn is a factor of n. Right? The same thing is happening here. If x is equal to 2 makes the function go to 0, then we say x minus 2 is a factor of the function. Here also, it's a similar thing. Putting xn equal to -1 takes the function to 0. That means xn plus 1 is a factor. But I have given you a formal proof. Now, what can I say about degree of DNF?
D minus 1.
Less than d minus, less than d minus.
Exactly. Now I can say that the degree is less than equal to D. Remember, DNF does not have any variable xn. So when I multiply DNF with xn plus 1, the degree has to increase by 1. It cannot remain the same.
So it should be equal to d minus 1.
Actually, yes, you are correct. This will be equal to D. I can be more precise. Not just that it is less than equal to D minus 1, I can say actually it is equal to D. If the degree of f is equal to D. Okay. Now, let's once again calculate the probability. With half probability, I will set xn equal to -1. What fractions is non-zero now?
0.
0. Now, on half fractions, I will set xn equal to 1. Like xn equal to 1 means half the fraction. For those, by induction, my function will be non-zero with probability
At least 2 power minus
To
d
the
plus
power
1.
minus of d.
This is again. Okay, this finishes the. What have we proved? If degree of f is equal to d implies probability that fx not equal to 0 is more than 2 to the power 9. Now, how is it important? Or this is the question we are asking. Okay, remember what? Do you remember what we wanted to prove in the beginning? What are we proving?
Degree is greater
At
than equal
least
to
log
omega
n.
log n.
Right, good. So let's go back to proof of min degree of f theorem. This was actually proven by Nissan and Zigady in 94. But yeah, let's prove how we are going to prove it. I'm going to bound the total influence. I'm going to say that if the function has small degree, then its influence should be big. But I know it cannot be bigger than degree. That's why I will get a bound. What do I know about influence? Influence is the probability that fx is not equal to f of x plus. This is by definition, but I can change this to say that probability DIF is. Is that okay?
Yes, sir.
Right? This is, we saw also DIF and LIF, they are same up to square. So whenever LIF is non-zero, DIF will also be. This is, by the way, the indicator variable for this was. Now, what do I know about the degree of DIF?
D minus 1.
D minus
Degree
1.
of F minus.
Right? Because influence I of F is non-zero, right? Influence I of F is non-zero, that means Xi appears in the Fourier expression. That means the degree of DIF is exactly equal to D. This implies this probability is greater than
2 to the power minus D minus 1.
Sounds good, right? So what can I say about influence of F? Influence of F is greater than
N times the summation is 2 to the power minus D minus 1.
yes. I know that all the variables have non-zero influence. That means for all the variables, influence is more than 2 to the power minus D minus 1. And what do I know? Degree of F is more than influence. This was the first idea. This implies D is greater than N times 2 to the power minus D. You can take log and you will see that D is bigger than half. Okay, this you can look at the notes also. It's not
So,
difficult. Yes.
Why can't we say that the degree is influenced by EIF? I mean, yeah, EIF. And
Why can't we say that?
degree is coming from EIF and not DIF. I mean, it might happen that.
Which
the
degree you are talking? I'm interested in the degree of DIF. I'm not interested in the degree of F.
No, that's what I mean. If say supposing degree of F is D, then by that expression, it might happen that degree of EIF is
Oh,
D.
right. You are right. Yeah. You are right. Thank you. That's a completely valid point. I should say that degree of DIF is less than equal to B. It might not be exactly equal to B minus 1 because the highest, I need not appear in the highest degree. Completely, but since it appears in a monomial, when I take the derivative, the degree will not go to, not degree, but the function will not go to Z. Right? So then degree is definitely less than equal to B. Right? That you agree. Very nice point. I can't say equality because I might not appear in the biggest monomial. That's the reason. Right? So yeah, but it doesn't matter for us, right? Once we know that degree is small, if it is smaller than D minus 1, then we will get a higher influence. So it is in our favor. It's okay. Right? So since degree of DIF is less than equal to D minus 1, the influence will always be bigger than 2 to the power minus D. And then the proof will go. Questions? Questions? Okay. Then we will finish the session.